Okay, guys, here we are. We're going to finish up 5.4, Fun with a Fundamental Theorem of Calculus. And let's face it, it is fun. Lots of algebra going on here. Remember, this Fundamental Theorem of Calculus Part 2 evaluates a definite integral. And we are looking for big F evaluated at 4 minus big F evaluated at 1. That is what this command right here is telling me what to do. But before I do that, I need to find big F, which big F means, hey, what is the antiderivative? Well, I don't know how to undo a quotient rule, I'm going to be honest with you. And because I'm looking at this and I can see, ooh, there's one term in the denominator of that fraction, hey, this is a strategy you're going to use quite a bit. And I'm going to make this 1 over the square root of u minus the square root of u over square root of u. I'm going to make it into two things you don't like, two fractions, du. And the whole point of that is so that I can simplify each fraction. 1 over the square root of u, that's u to the negative 1/2, right? And square root of u over square root of u is 1, and that's a du. So now I can find the antiderivative of that, u to the negative 1/2. Well, if I'm power rule anti-deriving here, well, I got to add 1 to the exponent, so that's u to the 1/2. And I got to think, what do I multiply a half by in front to get 1? Maybe a 2. Minus the antiderivative of 1, well, that's going to be u. And what I like to do is I like to look at this as 2 square root of u minus u. And then I'll evaluate it from 4 to 1. So I take my f of 4 minus my f of 1. Remember, this is going to be my big F of 4 here. This is going to be my big F of 1. And all I do is I plug and I chug. So that's 2 square root of 4 minus 4. And this is going to be 2 square root of 1 minus 1. What does that give me? Square root of 4 is 2 times 2 is 4 minus 4 minus square root of 1 is 1 times 2 is 2 minus 1. So that gives me 0 minus 1. My area is negative 1. Remember, my area can be positive, it can be negative, it can be 0, and it just may or it just may not represent the total area underneath the curve, okay? So the next thing we're going to do here is we're going to differentiate between how to find the total area of the region between f of x on the x-axis and on the given interval. We're going to call this a calculator problem. And to be completely honest with you, I could totally see this not being a calculator problem on the AP test. And the only reason I'm going to calculator this problem is because I just want to graph it easy. So I'm going to shut down here. I'm going to make a quick graph on my calculator, and I'm going to paste the graph of 3x squared minus 3 on the interval from negative 2 to 2 in a very nice viewing window. And as I'm doing that, why don't you enter it into yours as well? Okay, so I made a nice graph of this little bugger, and I kind of zoomed in. You know, I saw my interval went from negative 2 to 2, so I went negative 3 to 3. I could see my vertex was down there at negative 3. That's my y min is at negative 4, so I can see a little bit. I mentally plugged a 2 in there, and I saw that I'm going to go as high as these 2 points, and I can see 2 is going to reach up to my point of, what is that going to be, 12 minus 3 or 9, so it's going to get right up there to 9. And what I did was I just copied a cute little picture of that into my notebook here, so we can kind of see right up here. We're integrating from here. This is going to be negative 2 comma 9. And this point over here is going to be positive 2 comma 9. And what we are doing is we are finding this area from negative 2 to 2, okay, between the function and the x-axis. And we want to find the total area of it. Okay, and if this is a calculator problem, what a lot of people are going to do is they're not going to think, okay, they're going to say, oh, this is a really easy problem. I'm going to come over here to my calculator because it's calculator active, and what I'm going to do is I'm going to open myself a calculator page, and I'm going to add a calculator page, and I'm going to take, a menu 43, I'm going to go from negative 2 to 2 of my integral of 3 2x squared minus 3 dx, and they're going to hit enter and say it's 4, and you know what? You're going to be wrong. It's not 4. The integral is not 4. The integral is way more than 4, and if you notice here, okay, I have what I got going on here is I have some positive area here, I got some negative area here, I got some positive area here. So because that negative area took away from my positive area, the total area, everything, okay, the total area is not equal to 4. It doesn't equal 4, okay? The total area does not equal 4. And if I want the total area is actually, I think it's 12 is what the area is. And we just need to figure out what's the total area. So the easiest way to think about this is I can come right back to my calculator here again. Yep, because I like it. And I'm going to come up here and I'm going to copy that guy. And I know if I come back in here and I get to the, and I get there, and I'm going to put another parenthesis here. And the reason I want to put another parenthesis is so I can say, I think I can do this, absolute value of parenthesis 3x. And what that's going to do, that's putting that into the absolute value function for me. If I take the absolute value of that, that reflects that negative area on the top, and the actual area is 12, okay? And we just need to find out how are we going to find that, because I'll be honest, they might not even be asking what is the total area. The question might say, which of the following integrals give the total area for the given function on the interval -2 to 2. And the easiest way to do that is going to be taking the integral, the total area now, from -2 to 2 of the absolute value. And what I'm going to do is I'm going to shorthand this, and they allow this on the test. Rather than writing 3x squared minus 3, I know my function f of x is 3x squared minus 3. So I'm going to say the absolute value of f of x dx, and that's going to be 12, okay? That is just one way to do it, okay? What's another way that I can represent the area of this? And there could be multiple choices. Well, if I can see this parabola is very symmetrical, okay? So what I could do is I could give an option number 2, and I could say, oh, it's 2 times the integral from 0 to 2, okay? So if I kind of slice it in half and go 0 to 2 and double that area as an absolute value, okay, dx, that's also going to give me 12. That's another way. Well, that might not be a choice. There's all kinds of ways I can do this. Well, what can I do? Well, that's the question for you, but here's another option, okay? What happens if I took 2 times my integral from 1 to 2 of f of x dx, because I know those two, this part here is a positive area, and this part's a positive, and they're symmetric. And because I know this is a negative area, maybe I subtract the integral from -1 to 1 of f of x dx, because if I subtract a negative area, that turns it positive. Hey, there's an option. There's a third option. Well, do I have more options? You better believe you have more options, okay? Another option, number 4, another option could be, what? Well, maybe we're going to take 2 times the integral from 1 to 2 of f of x dx, the same way I did in number 3, and let's say, hey, we're going to add to that the integral, and we are going to reverse our limits of integration. We're going to go from 1 to -1, because now I'm making my delta x negative, and that would be an f of x dx, and that's also going to give me a 12. Okay, how about another one? All right, let's look at it. Maybe I want to take the integral from -2 to -1 of f of x dx. What's that going to do? That's going to give me this area. And maybe I want to subtract that area from -1 to 1 of f of x dx. And because I'm subtracting that area right there, I know I'm subtracting a negative, making it positive. And then maybe I want to add the integral from maybe 1 to 2 of f of x dx. Okay, that's another option. I got to be looking for all kinds of equivalents that can be in there. That area can be listed quite a few different ways, okay? And we just did 5 of them. All 5 of these, if you define f of x in your calculator right there, if you define that, you type all 5 of these integrals in, every dirty, rotten one of them should be giving you area of 12. Not should be, they will be if you enter them in correctly, okay? So we're going to come on to recall the Walk This Way lab. We did not do the Walk This Way lab, integrating any velocity curve. What we're going to do is I'm just going to throw a graph up here because we need to be able to figure out stuff with velocity and think of maybe your particles moving along the x-axis. I promise you, you're going to have one of those. And let's say I'm just going to give you a velocity curve here where I basically have feet per second on my y-axis and I have time in seconds on my x-axis. And I'm just going to move, oh, I don't want to do that. So I'm going to erase it and I'll change it later. I'm going to say seconds. And let's just say I have a velocity curve where I have both positive and negative velocity. And let's say I stop right here. And let's say I'm going to be integrating from 0 to, I don't know, let's call this 10, okay? And that means I would be looking for all of this area here, okay? If this is my my velocity curve. You know, remember, if I integrate velocity, I'm taking feet per second times seconds to get feet. I'm going to be getting a travel distance, okay? And what I want to do is, because I'm not going to have a function, and they like to do this, they're just going to come back here and they're going to say, okay, well, this area here, and we're going to call this, I'm going to throw a couple things in here for 6. That's going to be a 6. And this is going to be an 8. Nope, it's not drawn to scale. Don't worry about it. And we're going to say this area right here, that's going to be positive 8. This area right here is -3. And this area here, we're going to say is 5. And what they're going to do is we need to find the total distance traveled and the displacement, okay? I'm going to write this down quick, and then I'll be back. Okay, so they want us to find, and they're going to ask you to find, they're going to say, hey, find the total distance traveled and the displacement. And another word for displacement is simply going to be position. The displacement or the position of the object on the interval from 0 to 10. So the position is going to be, what position is this object going to be at after 10 seconds? And they're going to have to give you an initial position, and let's say it started at 0. But the total distance traveled, okay, what is the total distance traveled? Well, my total distance traveled is going to be represented by the total area, okay? Think about this. So if you leave school, you forgot your book, so 2 miles into the trip, you had to turn around and go back home and then come back to school. What was your total distance travel? Well, it's not just the distance from your house to school because you turned around and came back. You backtracked in there. So your total distance travel is going to be from 0 to 10, and the easiest way to do it is the absolute value of your velocity function with respect to time. That is going to give me the total distance traveled. And they might not give me a function, but my total distance traveled, well, what would that be? Well, think about when my velocity was positive. When my velocity was positive back in our particle problems, and my velocity is positive here, well, that meant I was moving to the right here, wasn't it? And when my velocity went negative, well, that meant here I'm moving to the left, and then I came positive again, so now I'm moving right again. But it doesn't matter, because if I move to the right 8 units, then I move to the left 3 units, and I move to the right 5 more, well, hey, isn't that 16? Isn't my total distance going to be 16 feet that the particle moved? Because everything, that's my total area. Okay, this is total area. Okay, so when I'm thinking of the other one, and what do you mean the other one? When I'm thinking of the integral from 0 to 10 of v of t dt, notice that one does not have the absolute value on it. That's going to give me my area. That's going to give me my net change, or thinking of it that way, that's going to give me the displacement. This is going to equal displacement of object from its, no apostrophe, I'm great at English, from its starting point. Okay, and if I think about this on the number line a second, I'm going to try to get this in here a little bit. So if I'm thinking here on the number line, if I'm starting at 0, okay, and what did I do here? Well, I moved to the right 8 units, and then from there, oh, I forgot, so I went back 3 units, and I'm there, and then what did I do? Oh, I went back 5 units. Where am I from my starting point if this is 0? Well, these 3, take off 3 of these and leave 2 on. Ah, I'm at 10. My position, my displacement would equal 10 feet in this case. So I'm only 10 feet away from where I started. I traveled a total of 16 feet, but I'm only 10 feet away from where I started. And you might not always start at 0. You might start at, let's say, started at 10. Well, if I started at 10 and I moved to the right 8, back 3, and to the right 5 more, well, what the heck would I be at? Well, I guess I would be at position 20. If I started, my initial position was at negative 10, and my net change, my net displacement here was 10 units, oh, now I'm back to 0, okay? So that's where we're at. And what we're doing is we are moving into the fundamental theorem of calculus part 1, problems and extensions, okay? This is going to make it feel like we are working in circles. And what I'm going to do, okay, what I just want to do really quick is the main thing we worked with fundamental theorem number 1 and number 2. Most of it we worked with yesterday and the day before was fundamental theorem number 2. And what fundamental theorem number 2 says was if I have the integral from a to b of little f of x dx, remember little f is a derivative of big F, okay? And that's going to equal big F evaluated at B minus big F evaluated at A. That's what we did. And big F is an antiderivative of little f, okay? And we will talk about big F and little f. And remember, this integral is going to equal a number, especially when these are numbers. These are both numbers. So when I evaluate my integral, I'm going to get a number, and that number can be positive negative, 0. Positive, negative, or 0. It could be any one of those three. And remember, it may or may not be the total area that we are talking about, because remember, the negative takes away from the positive and so forth, okay? So what we're doing is, today's big deal is today we're going to be looking more at Fundamental Theorem Part 1. And Fundamental Theorem Part 1 is really the understanding that the derivative of the antiderivative gets me back to where I started. It's kind of working in circles, and it seems kind of really weird and super confusing. It is a function defined as an integral, what we will be talking about today, and it is a big topic. Okay, it's a big topic in calculus on the AP test. I will promise you, you will have a few of these, and it is a really easy concept once you grab it. Okay, we're finding the derivative of a function defined as an integral today is what we're going to be doing. And all I'm going to do, come along for the ride. We are going to be taking the derivative of an integral. Okay, well, y here, this is my function defined as an integral. Okay, that's what this is. This is a function y, and it's defined, my y is defined as this integral right there. Okay, and what we're going to be doing is we're going to be just taking the derivative of these, realistically, okay? And whoa, what am I doing there? I wanted that because I want to get rid of these, and I want to get rid of this, and get rid of that, okay? So big part of today, huge part of today, is actually understanding that the derivative of big F equals little f, just with an x in it, okay? And my function defined as an integral. Well, just remember, this is what we've spent the last 2 days doing, and that is actually going to be right there. That's my area function, in which we could call capital F of x, big F, plus c. That's just another way to define that, okay? That's my function defined as an integral. So if y equals the integral from a to x of f of t dt, well, then what happens? Well, if I take the derivative of it, okay, if I take the derivative, I come back here, and I take the derivative of that guy. Well, the derivative of y is dy dx, and the derivative of the antiderivative is little f with x inside of it, okay? And what we're going to do is I'm just going to show this really quick using the Fundamental Theorem Part 1, okay? So my y actually equals the integral from a to x of f of t dt, right? Oh, what does that mean? Well, that means y equals, this is my area function. So the antiderivative of little f is, by definition, technically big F of t, but we're evaluating it from x to a, okay? And what that's going to do, that's going to give me, how do I want to write this? So that is actually going to equal f at x, right? Because we take that, we plug it in, minus big F at a, because we plug it in, and we subtract those two distances, or those two values, which means y technically equals big F of x minus big F of a. Now remember, a is a number. This is a number. This is my constant. That's my c value here. That's my number. And then if I came back and I took the derivative of this, well, what do I get? Well, the derivative of y is dy dx. The derivative of y in terms of x is dy dx. The derivative of big F, what is big F? Huh? That's big F prime of x to show a derivative, right? And then minus, oh, this is, remember, that's just a number. The derivative of that constant is 0. And what's another way that we could call big F? We're calling it little f with x in it. So dy dx actually equals the derivative of f with x inside of it. Just walking around in circles, walking around in circles. What? Well, I think you'll get the feel of it as we cruise along. Man, my eyes are getting badder. That's really blurry. But notice what your instructions say. Your instructions are telling you to do what? Find dy dx. Ooh, find a derivative. Okay. Well, what we want to be able to do is we want to be able to say, oh, the derivative dy dx, it's going to be 4x. We want to be able to do that. We want to be able to go straight from here to here. That's what we want, okay? It's a function defined. This is a function y defined as an integral. And to find the derivative of that guy, I don't even need to find the antiderivative, okay? But if I did, well, what's the antiderivative of 4t? I guess it would be t to the first, so it's going to be t squared. What do I multiply 2 by to get 4? Maybe a 2. So there's my there's my algebraic antiderivative. And if I evaluate it from x to 1, well, what is that going to equal? I'm thinking that's going to equal minus here. That's going to equal 2x squared minus 2, right? So technically this is talking about y equaling 2x squared minus 2. And what happens if I come back and I take the derivative of that? Well, the derivative of y is dy dx equals, what's the derivative of 2x squared? I guess that would be 4x. The derivative of minus 2, it's 0. And what we want to do, our goal is to find dy dx without having to do that. That's what our goal is, okay? Because the constant doesn't matter what it is. It's always going away because I'm taking the derivative of it. All right, let's see. Let's try another one. Well, if I wanted to find dy dx, that's saying take the derivative of that. Well, what's the derivative of y? It's dy dx equals. Well, what's the derivative of the antiderivative of 6t squared? I'm thinking it's going to be 6x squared. Because the derivative of my antiderivative is little f with x in it. There it is. And just to see it, okay, we'll do this one the long way again once. We're going to do this the long way home. So this is y is going to equal, well, I know the antiderivative of 6t squared. Well, that's going to be a t cubed, and 3 times 2 gives me that 6, right? And I need to evaluate that from x to 3 by gum, because that's going to give me my constant. Well, that's going to equal 2x cubed minus 2 times 3 cubed, which is going to equal 2x cubed. Well, 3 cubed is 27 times 2 is 54 minus 54. Hey, that just means this is my function. This is what it looks like when it's defined as an integral. Now I'm coming back, and I'm going to undo what I just did. The derivative of y is dy dx, okay? And that's what they want us to find, dy dx. That equals the derivative of 2x cubed. Well, 3 times 2 is 6. X, drop the power 1 to a 2. And the derivative of 54, it's 0. Again, I want to be able to take the derivative right here. I don't want to have to go through that. I don't want to have to do it. Why don't I want to have to do it? That's why. Because I don't know how to find the antiderivative of that. Now, if I think about it, it could be coming down. It's a combination. It almost looks like some type of arc sine. But I don't know. It's not, because that cosine on top throws things pretty wonky. But remember, I want the derivative of it. Okay, so I'm taking the derivative of this, which means the derivative of y is dy dx. And that's going to equal, okay, now remember, the antiderivative is going to be what? Big F with x in it. And then if I take the derivative of that, it's going to equal little f with x in it. Well, what's little f? Here's little f. I just need to put the x in. And that's going to give me cosine x over square root 1 minus x squared. There's dy dx. I'm taking the derivative of an antiderivative, and I get the exact same little function back, just with an x in it, okay? But, of course, things have to get a little bit more complicated. There it is again. Find dy dx. Oh, boy. This one looks a little bit different, doesn't it? And if we came here and we said, oh, find the derivative, and we say, oh, dy dx, that's going to equal, it's going to equal cosine x squared. Is that what it's going to equal? I don't know. Well, let's do this one longhand again. What is my antiderivative of my cosine? T, dt. Well, antiderivative of cosine, derivative of sine is cosine. So this is going to be sine t. And we got to evaluate this guy from x squared to 3. So this is going to give me really the sine of x squared minus the sine of 3. So y equals the sine of x squared minus the sine of 3. Well, what happens if I take my derivative of that? Well, the derivative of y is dy dx. That equals, what's the derivative of sine something? Sine something. Oh, that's cosine something times my derivative of my something minus, ooh, that's just a number. It's gone. Whoa, a little nutty there. Times the derivative of something. So dy dx actually equals 2x times the cosine of x squared. Ruh-roh. Those are different. Where the heck did that 2x come from? Came from the derivative of that guy, didn't it? Times 2x. What's the derivative of x squared? Times 2x. Hey, that's the chain rule going on here, ladies and gentlemen. Derivative of cosine something is, or the derivative of sine something is cosine something times the derivative of that something. So, well, why didn't I have to do that before? We did. What is the derivative of x? Derivative of x is 1. I can throw it times 1. It just doesn't affect anything. Same thing back here. What's the derivative of that? 1. I can say times 1. It's not changing it. I could go back 1 more. Ooh, what's the derivative of that? Times 1. Didn't change anything. And then I'm all the way back to my function defined as an integral. So we're moving forward. Hopefully you're making a little bit of sense out of this. And we are going to come to this next guy. And I have a little x cubed written in there for number 5. We're almost done for the day, ladies and gentlemen. So we want to be able to find the derivative without having to find the antiderivative. Oh, what do you mean? But explicitly, instructions say find dy dx. And the next thing that's very explicit is this is a function defined as an integral. So if I'm taking the derivative of an integral, well, think of order of operations. You do what's inside first. So I anti-differentiate, then I differentiate. I get right back where I started. So I want to be able to go d dx. Well, the derivative of y is dy dx. That equals, the derivative of the integral. Well, that's the derivative of the antiderivative. So that's little f. Now remember, that's little f of t in there. In the derivative, and when I integrate that, I get big F of t, and then I evaluate it, and that gives me big F with x in it. And then I differentiate it, and I get little f. And then, as I'm going through all this, then I get big F prime of x, which actually equals little f. Okay? With what? X in it. So here is my little f. So I'm going to take this and I'm going to say this is 4 with an x cubed in it times the derivative of that guy times 3x squared. What does that give me? It looks like 12x to the 5th is my dy dx. Okay? That should be the derivative of my function defined as an integral. Well, I'm going to do this I'm not going to say one last time. I'm going to do it another time. What is the antiderivative of that guy? Well, that's going to be t squared, 2t squared, evaluated from x cubed to 1, right? So that's going to equal this guy minus this guy. And the first guy is 2 times x squared, cubed, squared minus 2 times 1 squared, and that's going to be 2x to the 6th power minus 2. That is what my function really is if I integrate it with its constant and everything. If I come back and I take the derivative of that, well, the derivative of y is dy dx. That equals, what's the derivative of 2x to the 6th? Well, I got to take the 6 times the 2 and get 12x. I got to drop my power 1 to the 5th minus the derivative of 2 is 0. And what do you see? I see that the purple or the fuchsia line is way easier and faster than having to go through all of that crap, don't you? Okay, so that's where we're at. One more. Ooh, this one looks a little bit different. This is a little extension yet to this. So then, if y equals the integral from a to h of x to a function, for gosh sakes, of f of t dt, then dy dx has to equal what? Well, dy dx has to equal f with x in it times the derivative of what I put in. So that should equal y equals a integral from a to h of x of f of t dt. And we are going to prove that tomorrow. Well, I hope most of this made sense. We are going to actually prove this tomorrow at the beginning of class. And just remember, it's not mystical, it's not magical, it's mathematical. Thanks for playing math today. Talk to you tomorrow. Bye-bye.